So the next question is, the reaction goes through a trigonal planar intermediate, a triangular intermediate, a cyclic transition state with 4 atoms without any intermediate, or a square intermediate. Okay. So this can be confusing a little bit, but let us not get confused. Let us look at the structure as we have drawn it. So the major intermediate that we looked at had a positive charge on it, a methyl group and the cyclohexane. Okay. So remember that we had drawn this with some stereochemistry involved here, and the methyl group was on top. Okay. So if I ignore the rest of the molecule, this is going to be a planar molecule with a empty p orbital. Therefore, this would be a trigonal planar intermediate. Okay. So once you are sure about this, you do not need to worry about the other choices. So the next question is, which of the following is the most stable carbocation? So we have now moved to a different question. So the previous one is done. Now we look at a different question. So here the choices that are given, it's fairly straightforward. The way we would address this question is to assign whether it's a primary, secondary or tertiary carbocation. Okay. Since we have already studied that the order of stability of carbocations is tertiary greater than secondary greater than primary, then it becomes easy for us to address this question. So let us look at this one. So this has 1 hydrogen on this. This is a secondary carbocation. This has 0 hydrogens. So therefore this would be a tertiary carbocation. This again has 1 hydrogen. This would be a secondary carbocation. This has 2 hydrogens, and therefore this would be a primary carbocation. And this again has 1 hydrogen, and therefore this would be a secondary carbocation. Now looking at the order of what we had studied, all the secondary carbocations and the primary carbocation can be left behind, and the correct answer would be answer 4, which is a tertiary carbocation. The next question is, which of the following alkenes yield 3-bromo 3-methyl pentane as the major product? Okay. So let us answer this question by first drawing out what 3-bromo 3-methyl pentane looks like. So in order to look at this, let us first draw pentane. 1, 2, 3, 4, and pentane has one more carbon, that will be carbon number 5. Okay. So now the question is 3-bromo 3-methyl pentane. So on the third carbon there is going to be a methyl group and a bromo group. Okay. So in order for this to be formed, one would expect that the intermediate that leads to this would be a carbocation that has the following structure. Right. Now remember, let us make sure that the numbering is the same: 1, 2, 3, 4, 5. Right. So we are making sure that the numbering is the same. So if this intermediate, if this carbocation can be formed, then Br minus can attack and give you the product, which is 3-bromo 3-methyl pentane. Looking at these structures, I would argue that if compound 1 reacts with H plus, then it could generate this carbocation. If compound 2 reacts with H plus, right. Remember, the relationship between compound 1 and compound 2 is that they are cis trans isomers, but once we break the double bond, the stereochemistry is lost and you get a freely rotatable carbon-carbon bond. So both compound 1 and compound 2 would generate exactly the same carbocation as shown here. Okay. Now let us look at compound 3. Compound 3, again, if you react this with H plus, so if you number it 1, 2, 3, 4 and 5, it is going to give you the structure which has a positive charge on carbon 3. So this also is going to give you the same carbocation. Now coming to the structure 4, what might happen is that you can imagine that this reacts with H plus, and you would expect that you would generate, let us keep the numbering the same, 1, 2, 3, 4, 5. So, we have 1, 2, 3, 4, 5. The hydrogen is added here, and there would be a positive charge generated in carbon 2, okay, and there is a methyl group over here, just so that we complete this. So, this would be the major carbocation that you would form. So, therefore, this compound could actually add Br minus, but the other possibility, as we have studied, is that there could be a hydride shift, and that could give you the same carbocation, right. And therefore, I would argue that all of them would be capable of giving this as the major product during addition of HBr. And so, the answer is all of them. The next question is, which reaction intermediate is formed when Br2 CCl4 react with cyclohexene? Okay. So, we have studied bromination previously in the class. So, let us first look at the bromination. So, the starting material is basically cyclohexene. So, when you add Br2 to cyclohexene, then from our understanding of the mechanism, what we had proposed was that the Br forms some sort of an interaction with the pi bond, and it leads to the formation of a cyclic bromonium ion. Okay. So, it requires a 3-step process or a concerted type of mechanism, and you would end up with a cyclic bromonium ion plus Br minus. Okay. So, just to draw this out clearly, let me draw it out the following manner. I am drawing cyclohexane and Br going to be a positive charge and Br minus. So, this is called the cyclic bromonium ion. Okay. So, based on our understanding of the mechanism, we are already familiar with the formation of a cyclic bromonium ion. What we know further is that this is going to come and attack from the bottom face, and it is going to give you the following product. So, one of the Brs is going to be up and the other Br is going to be down. Okay. Now, let us go back and look at the answer or the choices that we have. So, if you see here, the correct choice is this as shown here, which is answer number 4. The next question is, which of these carbocations is most likely to rearrange? Okay. So, the rearrangement is a process by which a particular carbocation, which is to begin with a little bit less stable, and if a possibility of a hydride shift or a methide shift can occur, then it can rearrange and give you a more stable carbocation. Okay. So, in order to see this, let us first see what are the ones that are neighboring carbon. Let us take first structure here. Now, if you see this structure, we have as a neighbor 2 sets of hydrides. Okay. Now, it is possible that a rearrangement can occur, and this can give you a carbocation over here, right. However, the problem we may face is that this structure to begin with has a secondary carbocation, and after rearrangement it ends up with a secondary carbocation. So, I would argue that this is less likely to rearrange. So, I am just going to write less here so that it's clear. Now, let us look at the second case where we have this particular carbocation over here, and just to draw this, this is a secondary carbocation again, right. And what we would expect is that there are two hydrogens next to it, and if either of these hydrides migrate, it is going to end up with another secondary carbocation, which I am going to draw here. Okay. However, this would be less likely, but if one of the methides migrate, then you are going to end up with a tertiary carbocation. So, therefore, I would argue that this is more likely to rearrange. Now, let us look at the third case. So, again here this next to it is two hydrogens here and two hydrogens here. By rearranging, it is only going to produce another secondary carbocation, and therefore, I would argue that this is not very likely either, okay, less likely. And the last case is a case where you have a carbocation on a primary carbon, and right next to it there is a methide. Okay. So, it is possible that either the methyl group migrates, or it is also possible that this cyclohexane can migrate, right, and both of these will end up with a more stable carbocation. So, therefore, the correct answer is that this and this are more likely to rearrange, whereas this and this do not gain any additional stability by rearranging. So, the correct answer would be 2 and 4. So, the next question involves methyl cyclopentene. So, again let us number these carbons 1, 2, 3, 4, 5, and there is a methyl group over here. So, this will be cyclopentene, and the reaction that we are going to look at is the reaction with Br2 in the presence of methanol. Okay. So, the first question here is the major product of the reaction is or are the following, right. So, in order to address this question, let us first draw out the structure once again. So, you have cyclopentene with a methyl group, and this reacts with Br2 in the presence of methanol. Okay. So, the assumption we will make here is that methanol is actually a solvent, and therefore, it is present in a very large excess. So, as we are quite familiar, the Br2 would be expected to react in a way that it would form a cyclic intermediate, which is known as the bromonium ion. Okay. So, as far as the stereochemistry is concerned, if the Br2 approaches from the bottom face, right, then we would expect the Br to be here and the methyl group to be up. Okay. And similarly, if it approaches from the top face, you would expect the Br to be up and methyl group to be down. Let us draw out the other structure where the methyl group is down and the Br is up. Okay. So, this is the other structure that is possible. However, you will quickly realize that if we just rotate this the plane below, then you will get the following structure. So, let us make sure that we number the carbons correctly 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4 and 5. Okay. So, let me draw the product after rotation. So, what I am doing is I am going to rotate along this line and rotate it in the following manner. So, the cyclopentane remains the same, the carbon 2 goes up, carbon 3 goes up, carbon 4 remains the same, carbon 5 is in the below, and carbon 1 is over here. So, what I have done is I have just rotated it like this. Okay. So, now what happens is that the Br is going to be below the plane, and in the case of this, the carbon 1 which has the methyl group is going to go up. Okay. So, if you compare this structure and this structure have a mirror plane relationship. Okay. So, therefore, these are actually enantiomers. Now, if you look at it, the attack of methanol can happen from either carbon 1 or carbon 2. Okay. So, this is the choice that we have to make. So, let me draw out the bromonium ion once again, CH3 up here, Br. So, let us take this molecule and react it with methanol. So, CH3OH is present in very large excess. So, it is going to attack from the top face and you would end up with the methanol forming intermediate in the following manner, where you have OH CH3 plus, and since the attack happens from this phase over here, the methyl group goes down and the Br also goes down. Just so that I do not get confused, I am going to continue with the numbering 3, 4 and 5. Similarly, 1, 2, 3, 4 and 5. Okay. And this will of course lose a proton and give you OCH3 with a methyl group down and a Br down. Okay. Now, you can think of the other possibility where this actually reacts and it will give you exactly the opposite product. Means you will end up with methyl group up, OCH3 down, and the Br will always be opposite to the OCH3 because the methanol is going to approach from the opposite face. So, therefore, I would expect that these two would be the major products. Now, let us also consider the possibility of attack on the other carbon, right. And why am I saying that this would be the major product is because one would assume that the more stable or the carbon 1 is better capable of handling a positive charge compared to carbon 2. And so, when the bond breaks, the carbon 1 will have a delta plus on it, and that is going to be more stabilized, and therefore, the pathway leading in the direction where a carbocation or a pseudo carbocation is formed on carbon 1 would be more favored. Now, let us look at the other possibility where the methanol attacks from the opposite face on the other carbon. So, you will end up with this product and these two products you will end up if the methanol attacks on carbon 2. Okay. So, now let us look at the choices that we have. The OMe over here, Br over here. So, here the relative stereochemistry is absolutely correct and we would expect that this product would be formed. Now, let us look at this over here, the Br is here and methoxy is over here. So, here what we see is the attack happens on carbon 2. So, if I have to label this, let me label in the following manner. And so, attack happens on carbon 2, which we have already said would be less likely. And now, in this case, the Br ends up on the same side as methoxy. So, the labeling of the carbons is correct, which according to our mechanism is not possible. And the last case where we have again, we have the right carbon over here, 1 and 2, and here the methoxy attacks on carbon 2. So, therefore, this would not be possible. This according to our mechanism is not possible. This because of the attack on carbon 2 by methanol is not possible. Therefore, the correct answer is 1 only. Okay. So, the next question is the reaction goes through what kind of an intermediate. So, here are the choices that are given. We already know that the mechanism goes through a bromonium ion, which is a triangular intermediate. The next question is, the major products of this reaction have the following relationship. So, I will let you go back and draw these structures on your own, and the correct answer is that they are actually enantiomers of each other.